Okay, hello everyone. As many of you already know, my name is Catalán, and today I'm going to present the results of my doctoral thesis progress in this presentation called Unsteady Flow Simulations with Application to Particle-Laden Flows in Aerospace Engineering. So why are we interested in particle-laden flows? Mainly because they exist widely in nature engineering applications, as sediment transport, aerosols, spray applications, biomedicine. But of course, in aerospace engineering, we have several applications, as it is the case of solid propellant rockets, as we see in the figure on the right, also gas turbines and combustion chambers, high-speed flights, is the one we can have on the Earth atmosphere and the most high levels, and also in more specific problems, as it is the entry into Mars atmosphere, we see in the figure that we have in here. This is a case of a simulation with a lot of particles as well that play an important role. Today, however, we're going to be focusing on dilute particulate flows, which are usually flows in which clouds of particles are immersed into an ambient fluid, as we see in the figure that we have here. In these flows, usually the relative distance between particles is large, but however, particle fluid aerodynamic interactions play an important role and can eventually lead to lateral motion, vortex shedding, and so on, right? This, at the same time, can potentially give rise to collective effects and triggering of the turbulent motion. So, in this study today, we're going to be keeping this into consideration, and we're going to address a simplified problem in which a single spherical particle is going to settle in an ambient fluid under the effect of free stream perturbations, right? So, taking a look to this particular problem in which the single particle settles in ambient fluid, if we take a look to the literature, we know that the problem is governed by two non-dimensional parameters, okay? Galileo number and density ratio. The Galileo number is nothing else than a Reynolds number whose characteristic velocity is this gravitational velocity that is defined here, okay, dependent on the gravity, the sphere diameter, and the density ratio. And of course, the density ratio is the ratio between the density of the particle and the density of the fluid. Okay. So, from the literature as well, we have this diagram, this map, in which we are able to see that there exist several particle motion regimes depending on these two non-dimensional parameters, okay? On this density ratio and Galileo number, okay? Today, we're going to study the case of density ratio 1.5, in which, of course, the density of the particle is higher than the density of the fluid, okay? For this case, we are able, in the literature, from the literature, we know that there exist several particle motion regimes, okay? Depending on this Galileo number, first of them is the steady vertical regime, in which the particle settles vertically. Then we have steady oblique regime, oscillating oblique regime, and chaotic regime, okay? So, the objective of this study is to address or analyze how these ambient perturbations modify these regimes. And today we're going to be focusing in how the perturbations affect to this first regime, which is the steady vertical one. In order to do so, we have performed simulations with our in-house Navier-Stokes solver, Toucan, which solves the presence of the immersed body using the immersed boundary method proposed by Ullmann. And also we are including the effect of free stream perturbations with an additional source term, this F stick to the equations at the end, in here, okay? Following the work of Schmidt and Breuer. So this last term, which is as said, including the equation, is going to be a function of the integral length scale of the perturbation, of the intensity of the perturbations on the time scale that we want to have, and of the string-wise injection location. Of course, since we want the particle to be settling and we want it to be free to move, let's say, we are solving the dynamics of the particle as well by solving the Euler-Newton equations, which we are coupling with our Navier-Stokes solver. Okay? So then having the flow solver and coupling it with the particle motion, we are able to solve everything. But how do we compute this source term that generates the perturbation? So this source term, we have to distinguish that there is a random part, which is u prime, the perturbation velocity, and we have another part that depends on the injection location, on the scales of the perturbation. And the main idea here is that we want to generate a signal that is going to be self-correlated, okay? This signal is going to be u prime of t, and we want to generate this signal, okay, according to the scales that we want to impose. So, in order to do so, at each time step of our simulation, we are basically going to compute each of the points of this time signal. Okay? For doing so, we need a set of random numbers that we want to filter. Right? We're going to filter using a Gaussian filter, whose filter width is going to be, of course, intimately related with the size of the perturbations that we want to implement. Once, of course, by applying this filter, we are somehow fixing the integral scale of our perturbations. Okay? Then, in order to introduce new randomness in our procedure, at the end of each time step, we are generating new random numbers, and we are creating a circular shift in the set of random numbers that we are filtering. So at each of the time steps, we are randomly changing our perturbation, of course, which is something what we want. In the end, the generation of random numbers is only done in the first step, and then for the following time steps, we are just looping on the second and third steps, because the last steps is renewing our random numbers. So several additional comments in here are that the time and stringwise direction are here equivalent by the Taylor hypothesis, okay? That this has to be done in 3 dimensions, because we not only care about the stringwise direction, but also care about the lateral directions, y and z, following the work of Kempf. Also, the random numbers that we are generating are generated with a standard deviation equal to the intensity of the perturbation that we want, okay? Finally, as a consequence of how we are filtering, the integral length scale of our perturbation is actually an input of our simulation. If we follow the definition of integral length scale, is directly the input scale that we are putting. And also, finally, we are going to use homogeneous anisotropic perturbations, turbulence, okay? Which basically means that the sizes of the perturbations in the 3 dimensions is going to be the same for my simulations. So once we have this u prime computed, the random part, we basically are going to compute the whole source term, right? So what we are going to do is extend this injection plane over a 3-dimensional region of our domain, okay? Delimited by the center of the region minus the scale of the perturbation that we want to reach, and plus the scale of the perturbation that we want to reach, as we see here, okay? The time scale is also used as a relaxation time to preserve the autocorrelation. So in the end, we're going to end up having a source term which is going to be of like this. Okay? Also, by using these source terms, we take advantage of the fact that we can locate our influence region in the vicinity of the flow, of the body, of our region of interest, where usually the grid is much finer, right? By doing so, we can avoid, of course, problems related with the coarseness of the grid that usually appears in regions that are usually at the inlet, for example, and so on. So, regarding the computational setup of the simulation that I'm going to be showing, we have basically the sphere located somewhere in the middle of the domain, okay? The boundary conditions, we have applied periodic boundary conditions for all the lateral boundaries, that is, all the boundaries in y and z directions. For the inlet, we have a Dirichlet boundary condition, and for the outlet, we have an advective one, so that we are able to have an outflow, okay, from the domain. The cases in we're going to focus today are the cases in which we have 1% of intensity of the perturbations, a size of the perturbation, an integral scale of 1.137, which is, of course, near to the being 1 the diameter, because I'm talking about non-dimensional quantities, okay? But of course, we are running at the same time simulations with 3% of intensity and with different sizes. So first of all, I'm here showing a case with no perturbations for the sake of reproducibility, in which we basically are able to capture the steady vertical regime, which is the one in the literature, okay? That we know from the literature. In here, we first focus on the particle position evolution over time. We clearly are able to see how it is, the evolution is fully horizontal, so this means that we are perfectly capturing the regime. Also, if we take a look to the two-dimensional slices of vorticity, we are also able to see that the wake is fully axisymmetric, so this is perfectly captured. Also, we are showing here some three-dimensional isosurfaces of stringwise velocity and Q criterion to see the vertical structures. And we are able also to see how they resemble very well to the ones that we have from the literature, that are those ones, right? Now in here, I'm showing one of the cases of free string perturbations. The very same case with Galileo number, sorry, I forgot to mention, with Galileo number 150. That is the one corresponding or in the interval of steady vertical regime. But in here, of course, we are including perturbations of the size that I was mentioning and of 1% intensity, okay? What we see here, if we take a look to the particle position, we see that, of course, the steady vertical regime is no longer happening, right? We have a lot of motion in there because of the presence of the perturbation, and what we see is that somehow the particle, due to the regime in which we are, is trying to follow the steady vertical regime that I showed before, but it is unable to follow because of the perturbations. So in the end, the particle, I've shown snapshots here of some of the convective times of our simulation that I've run. This ideally would be better shown in a video, but we are able to see, for example, here that the particle that started at the origin, okay, has moved near to the boundary and so on. And also we are able to see these three-dimensional vertical structures in which it can also be appreciated that the wake is fully broken. We can also see the perturbations in sections that are located string-wise, okay? The perturbations advected through the wake. Now I'm showing the very same simulation with the objective to somehow assess the effect that has the particle rotation in the motion dynamics of the particle, let's say, okay? In order to do so, we have departed from the same condition that we showed before, but we have restricted the rotation of the particle so that the rotation is 0 for the simulation, and by doing so, we are somehow able to investigate a little bit more on what is the reason behind this lateral motion of the particle and so on, okay? So what we see here are, of course, different results, okay? In spite of the fact that we have the same kind of perturbations, the perturbations are randomly generated, okay? In spite of the fact that we are starting from the same conditions, in the end, when the simulation evolves, the perturbations generated are fully random, so in the end, the simulation is completely different, okay? And also take into consideration that we are restricted the velocity, the rotational velocity. So in the end, what we see here is similar. We see a lateral motion again. We see the wake is fully broken in the three-dimensional case as well. We see some oscillatory patterns in the two-dimensional wake, in these slices, and the evolution of the perturbations is, of course, the same or nearly the same that we had before. So, conclusions of this study. Well, we are able to say that in the presence of flow perturbations, okay, of the kind we are studying, of this size 1.1 and intensity 1% at Galileo number 150, the steady vertical regime is no longer captured, right? Instead, what we have is more or less an unsteady quasi-vertical regime. Okay, it's trying to follow the regime, but it is not able to do so. And we have transient and steady oblique regimes that appear. For example, if we see the evolution in the z direction, we have these transitions, okay, in which the particle moves in an oblique way. Also, this part, this is with the rotation allowed, and this is with the rotation restricted, in which we have, of course, this transition as well for quite a lot convective times. So next steps for this. Also, we are more or less, in principle, we are able to see that there is no apparent effect of the sphere rotation in here. Okay. So then next steps of this study could be, of course, continue varying perturbation and see what happens, which we are already doing actually. And, of course, trying different regimes, increasing the Galileo number, for example, trying including perturbations, Galileo number of the oblique regime, oscillating oblique, and so on. This is a case that I've run. This is a three-dimensional vertical structures for the case without perturbations of oblique regime. Finally, I have a slide with the main contributions of my work. That is mainly the development of the code that allows the generation of free stream perturbations in our parallel flow solver, Toucan. There can be several applications to this, as it is the case of particle-laden flows, which I'm explaining today, but also in aerodynamics. For example, I'm right now supervising a bachelor thesis that goes in this direction, in the effect of the aerodynamic performance of an airfoil subjected to perturbations, and also in bioinspired flows, okay? And well, I have some of the contributions. I presented a research poster last year, and I'm gonna be present in 2 conferences. Actually, one is next week, and the other one in September. So that will be all from my side. Thank you very much.